We just finished vector kinematics. Kinematics is the study of things that move. Vector kinematics, you'll notice there was a lot more two-dimensional, triggy stuff in Physics 12. But really, I didn't show you anything new. It was all taking Physics 11 and expanding on it. Unit 2 is vector dynamics. Dynamics is the study of what makes things move. Forces. And much like last unit, the first 3 or 4 lessons ideally will be review, cake, with some extra Physics 12 icing added on. Oh, hadn't thought of that, but that makes sense. And then all of a sudden, Grayson, you're going to see we give things a tilt. We go at angles, and we go two-dimensional. So, review, if you know this, good, but I always assume you've forgotten everything. A force, I wrote, is a push or a pull. It is a vector, and it has a magnitude measured in units of newtons. Forces are based on interactions between two objects. Some important forces that we're going to study in this course include the following. What did we call the force that was the Earth pulling on all objects downwards towards the planet's center? What did we call that? And the symbol I use for that is F with a subscript of G. What was the force that we called, which was the microscopic hills and valleys that between an object that interlock and prevent it from sliding along a surface? Okay. Most textbooks call it FF. For some reason, I don't know why, I almost always call it FFR. The R is optional, but for some reason, years ago, I started picking, I guess, for friction, but whatever. There's my symbol for friction. Who remembers, what did we call the force that was the surface pushing up on an object, also the apparent weight of an object? Normal force. Don't write this next bit down. Many textbooks will call it for normal. The problem is that also looks like north and newtons. I don't like that. Some textbooks will call it for weight. The problem is that's not always consistent. So I use normal force. Several years ago, we were marking Physics 12 provincial exams, and there was a question that said, find Fn, the normal force. And we were marking papers, and a student wrote, which was funny. It didn't give them any marks, but it was funny at least, okay? Fair enough. Points for honesty, but not for physics. The force from a stretched string or rope, which is constant throughout the string or rope. I like it when I lose tension. Makes me relax. That one typically I symbolize with a capital T, although once in a while you may see me symbolize it with FT, especially if T is being used by something else. And T does mean something else in particular in the, well, patience, you'll see. What was the contact force from an external agent or outside agent, usually a person? This one's in a bit more obscure. This is the one that we called the applied force. That was we didn't bother drawing what was causing it in the diagram. We just drew an arrow to represent that it was being caused. And my symbol for that, Jordan, is traditionally FAP. What is the force of resistance from the air opposite to the direction of motion? Well, technically it's called drag, or air resistance. And there is a symbol for it, but I am going to treat it mathematically this year as though it's air friction. So I'm actually just going to label it. Now, to be honest, what I'll do is I'll often call it F air, but I'll treat it temporarily sort of like friction in my free body diagrams. FFR. And then the last one is not a force per se, but it's actually the vector sum or the resultant of all of the forces acting on an object. Do you remember what we called that one? It was a three-letter word. Began with the letter N, then an E, F net. When we talked about the net force, what we really meant was if you added up all of the forces acting on an object and represented them with one vector, that is F net. It never actually appeared on the free body diagram. It was if you listed all the forces on the free body diagram, what you would get if you added them all up and represented them with one. But we found it much easier to keep all the small forces on the free body diagram. Now we come to Newton's laws, and I got to go on my Sir Isaac Newton rant. So Newton's first law says, and he phrased it in Latin, Grayson, every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Huh? Here's what it says. The only way that you can accelerate an object, or if I even want to break it down further, or change its velocity, because acceleration is defined as a change in velocity over a change in time, is to apply an unbalanced outside force. And it works backwards. If an object is accelerating, you know there must be an unbalanced outside force. If there's an unbalanced outside force, the object must be accelerating. Oh, if it's not accelerating, and remember, Josh, not accelerating can mean at rest or going in a straight line at a steady speed, then the net force on that object must be zero. Has to be. Has to be. This is often called the law of inertia. What's inertia? Oh, we have Calvin and Hobbes explain Newton's first law of motion in your own words. Yakafub Mog, Grug, Pubawump, Zinc, Watum, Gazork, Chumble, Spuzz. Newton's first law of motion in his own words. He met the criteria. Don't try that on a test with me. What is inertia? I'm picking my words carefully. The amount of mass an object has is a measure of an object's inertia. Inertia is that which resists a force. And what resists a force? Mass. Newton's second law. This is the equation that Sir Isaac Newton came up with. Hey, F equals what? MA. I should, full disclosure, he never phrased it this way. He was much more interested in acceleration and momentum, so he actually phrased this to get momentum by itself, and it had a force equation in it. But traditionally now we just say F equals MA. This one is on your formula sheet. You'll memorize this one because you get tired of looking it up so often. Newton's third law is often called the law of action-reaction. It's usually stated something like, for every action, there is an equal and opposite reaction. Mr. Goulet likes to say that. And to me, that's about as confusing as you could have phrased it. Huh? Here is Mr. Dueck's version of Newton's third law. Forces come in pairs. You cannot have a force all by itself. Now, you may have a force by itself in your free body diagram, but that's because you're only drawing the forces on object A. But I'm telling you, there would be an identical force in the opposite direction on object B if you had drawn object B in your diagram. In fact, as an equation, I say this. F of A on B equals negative F B on A, where negative is the vector direction. Where negative is the vector direction. Okay? Why would an athlete want low mass shoes? Okay. A equals F over M. So let's look at Usain Bolt. Let's suppose Usain Bolt has trained and lifted weights as much as possible, so he has maxed out the force. How can he increase the acceleration? What other variable could he change that would give you a bigger acceleration for his feet? Make M smaller. Like make that, and you're seeing that more and more in the Olympics. It's often coming down to hundredths of a second due to equipment, right? A force with which you have had some experience is the force of gravity between you and the Earth. This force is also known as weight, and it's measured in newtons in the metric in the SI system, or pounds in the old imperial system. The force of gravity is not the same thing as mass, although they are related. Mass is how many atoms, it's the amount of matter in an object. Really, it's how many protons, neutrons, and electrons make up an object, measured in kilograms, or slugs in the imperial system. To relate mass to force, we need to know the number of newtons of force per kilogram of matter. We call this the gravitational field strength. And our symbol for it is a lowercase g. Near the Earth's surface, g is 9.8, negative if you want to call it downwards. On the moon, g is 1.6. Now, what else have you called 9.8? Where else did that appear in the last unit? Acceleration, meters per second squared. It also turns out it's 9.8 newtons per kilogram. So we said this last year. The force of gravity, as long as you're close to the Earth, was mg, where g equals the gravitational field strength. A synonym for which, it turns out, Rafi, is acceleration due to gravity. We also broadened it last year into Newton's universal law. That applies it does apply on the Earth, but this is a shortcut. When you're off the Earth, then you can use Newton's universal law to figure out what the force of gravity is anywhere. But as a convenient shortcut, if you're near the surface of the Earth, take the mass times by 9.8, there you go. So example 2 says, find the weight of a 10 kilogram object A on the Earth, B on the moon. Okay. For both of these, it's going to be mg, except it'll be g on the Earth versus g on the moon. What's the mass? Well, in each situation, it's 10. What's the gravitational field strength on the Earth? 9.8 newtons on every kilogram. Naomi, without a calculator, in your head, timesing by 10, what's 10 times 9.8, please? 98, thank you so much. What's the gravitational field strength on the moon? 1.6 newtons for every kilogram of mass. Naomi, in your head, timesing by 10, what's 10 times 1.6? 16 newtons. I'll leave you alone now, but it's your 10 times table. Oh, okay, sorry. Okay. So on the moon, 10 kilograms would tug down towards the surface with a force of 16 newtons or 1.6 newtons on every kilogram of mass. On the Earth, it tugs down with 9.8 newtons on every kilogram of mass, so for a total in this case of 98 newtons. Next page. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. It says this: if a force of gravity acts on an object, then the object A remains at rest, B moves at a constant speed, C accelerates in the direction of the force, or D, all of the above. So you're going to vote. Ready? Who says, oh, and again, how high you hold your hand up is how sure you are of the answer. If the force of gravity acts on an object, then the object, Dueck, obviously, A, remains at rest. No one. B, it moves at a constant speed, Mr. No one. C, Mr. Dueck, free fall, it accelerates in the direction of the force. No one. D, it can be at rest, it can move at a constant, okay. Convince me. Can you give me an example where A is correct? Look left. Look right. Every one of you. Is gravity acting on you? Are you falling into the ground? Are you lifting into the air? You are at rest? Okay, so I'm going to say this then. A, sitting in a chair. Can you give me an example where B might be correct, where gravity could be acting on you while you're moving at a constant speed? Is there a way that you could be, well, here's what I'm going to say. When I jumped out of an airplane, eventually I jumped out of an airplane. When I jumped out of an airplane, initially I was accelerating, but there came a moment where eventually air resistance up and gravity pulling me down canceled each other out. I was free falling at a constant speed. And we have a name for that. We call it terminal velocity. Terminal because you're no longer accelerating. Your acceleration has terminated. Terminal because if you hit the ground that fast, you're terminal. Right? Can you give me an example of how C could be the case? Vacuum 2Cs, vacuum's 1C, 2Us, right? Free fall in a vacuum, or free fall before you hit terminal velocity. Since A, B, and C are all right, D must be correct. Sure, there's a good explanation. Give me an example that each one is right. Good enough. Someone was going to change their mind. I heard that. No, I like that. D is good. Newton's second law says, I've been meaning to correct this for 10 years and I still haven't. First law. And every year I still have. Are you really, Kelvin? You haven't corrected that yet? Jeez. Note to self. Okay. Newton's first law says this. If you have all your forces balanced and canceling out, the object is either at rest or moving in a straight line at a steady speed. It's not accelerating. Objects in motion remain at motion, or objects at rest remain at rest. If you have unbalanced forces, you must be accelerating. Oh, and I can be more specific, in the direction of the unbalanced force. So, F net, or sometimes you'll see, does anybody know what that symbol there means? It's a fancy schmancy symbol. We're going to be using it later on this year. So, it's typewritten like that. It's often just handwritten like kind of a capital M on its side. And that means the sum of. So that's saying the sum of, if you add up all of the forces, that's your net force. F net is not a real force. It never appears on an FBD. Who remembers from last year what an FBD stands for? Okay, it'll never appear. F net will never appear on my free body diagram. It will be if you erased everything on the free body diagram, added all the vectors up tip to tail, and summarized it with one force. It's what you could have drawn, but we'd much rather see all the individual forces. So you're going to hear me always go on a rant, don't put F net on the diagram. It's one of the most common mistakes. And then kids, when they're solving, have an extra force that wasn't supposed to be there and don't know what to do. Why? It should be moving. Little note, by the way, newtons per kilogram is the same as meters per second squared, which is why the acceleration due to gravity is 9.8 meters per second squared, and the gravitational field strength is 9.8 newtons per kilogram. As a proof, 1 Newton is mass times acceleration, so 1 Newton per kilogram is mass times acceleration divided by kilogram. Oh yeah, newtons per kilogram is meters per second squared. So another term for acceleration due to gravity, and they're interchangeable, at least at this level, is gravitational field strength. Measured in newtons per kilogram. What's the gravitational field strength of the Earth near its surface? 9.8. What's the acceleration due to gravity near the Earth's surface? 9.8. You can put a negative in front if you want a vector, although this unit will often ditch the negative because we'll let negative and positive be whatever's most convenient. It says find the unbalanced net force in each situation. Include direction. Let's go north, east, south, west. What is the unbalanced or net force in A, magnitude and direction? And it's meant to be fairly obvious as a start. Zach, what's the unbalanced net force in part A?
2.
Direction? Yeah. 2 newtons. I'll put an at east so it doesn't look like 2 northeast. Not enough letters in the alphabet. North and newtons look the same. What would the net force of part B be? 3.7 newtons south. Ooh, what would the net force on object C be? 1 Newton north. So we're doing vector math. What about vector D? The net force would be 5 newtons due east. What about diagram E? First of all, north-south, what's my net force? 0. So what's my acceleration north-south? North-south, what's my net force? 0. What's my acceleration north-south then? 0. So either we're not moving north-south at all, stopped, or we could be moving north-south at a constant speed, never changing. I need more information, but either of those would be acceptable. So what's my net force overall here? What about for diagram F, if y is bigger than f? What's the direction of the net force? South? What's the magnitude? How would I calculate it? And this this is going to bring us to our winner minus loser method of treating forces as though they're having a tug of war. We will decide to let whichever direction has the biggest force, the net force, we'll say that's positive, that's winning. Everything else will be negative, losing. To solve force problems, we are going to draw free body diagrams, FBDs. You draw one arrow for each force that acts on an object. F net never appears on your free body diagram. Label your arrows. Put your tail of the arrow at the center of the object if you can. I wrote acceleration and velocity vectors should be drawn differently from force vectors. From force vectors. You can use wiggly lines or whatever. I rarely put velocity or acceleration vectors on a free body diagram. Use the free body diagram to write an algebraic net force equation. And then solve for any unknowns. We're going to solve our net forces by using a tug-of-war analogy. We will ask ourselves, all right, which force is winning? And we're going to say, winner, take away loser equals F net. Although we'll start to take shortcuts, Jordan, because F net is always just going to be ma, because that was Newton's second law. F net equals ma. This is going to allow us to avoid having to decide which directions are positive and which directions are negative. Josh, it's also going to allow us to avoid minuses, which is where we're likely to make a mistake. We will decide in this unit which direction is positive, which means that 9.8 won't have a negative in front of it, like it did last unit all the time. Example 5. A 2,000 Newton rock hanging from a rope accelerates upwards at 3 meters per second squared. Okay. A says, draw a free body diagram. We represent the rock with a dot. There's the rock. What are the forces acting on this rock? Get the obvious one. Okay? I am big on get the obvious ones first. So I have gravity pulling it down. What other forces are acting on this rock? The rope, and we've decided that we're going to call the rope what? Tension. Now, before I draw it in, which way is the rock accelerating? Up, down, or not accelerating? Up. So which force must be winning? Up or down? Up. And that's going to be tension. Joseph, I'm going to exaggerate tension very long so that clearly I can see that it's winning. I did A and B together because B said compare the forces that act on the object. I did do that with my arrow lengths. Write a net force equation. Okay. Who's winning? Who's losing? The equation's going to look like this. Winner minus loser equals ma. Josh, what does part D want me to find? How would I get the tension by itself in my equation, folks? Plus the mg over? So I'm going to get this. Tension equals ma plus mg. All right, let's see if I can go further. Tension equals, did they tell me the mass of this? Ooh, they didn't. What did they give me here? This is mg. So certainly I can go plus 2,000. That's mg. I don't need to multiply it by 9.8. How do I know? Because what are the units next to there? Newtons. It's a force. Right, Rach? Oh, and they did tell me A, the acceleration. Rachel, what's the acceleration? So I can put a little 3 right here. If I know the weight, 2,000, How can I find the mass? You know what? I'm going to write then 2,000 over 9.8, because if I have to do it once on my calculator, why don't I just do it in the equation, and that way I'm not rounding off at all. The tension in this rope is 2,000 times 3 divided by 9.8 plus 2,000. The tension in this rope is 2,610 newtons. That's to 3 sig figs. Example 6. Is it correct to say that if the rock in example 5 is moving upwards, then the string tension must always be greater than the weight of the rock? What was the weight of the rock in newtons? What was our tension that we solved for? 2,600. So it certainly is greater. Does it always have to be greater? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Who says, yeah, I've thought about it, Mr. Dueck. It always has to be greater. If we are moving upwards, it always has to be greater. No one. Is that a hand up, Zach? Okay. Who says false? 1, 2, 3, 4, 5, 6. Okay, so who chooses to wimp out? 8 or 9 of you. Convince me. Can you give me a situation where the rock could be moving upwards and tension wasn't greater, where tension was identical? Yeah. What if that was the case? Let's look at our equation. We said tension equals ma plus mg. Constant speed means which of these is 0? But what were you looking on Siri for? I think that's a Timbit. And I haven't forgotten that I haven't given these ones away. Back here, folks. Okay, if we have a constant speed, A is 0, and we have tension equals mg, which means it's not greater than mg. So if we were going up at a constant speed, I can see how we could get it equal to, therefore this statement is false, because this said it must always be greater. Nope, I can make it the same. Yeah? Okay. What about for this same rock moving upwards, is it ever possible for the chord tension to be less than the weight of the rock? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. Who says it is possible for tension to be smaller than the weight of the rock? Who says, no, it's impossible for it to be smaller than the weight of the rock? Convince me.
Oh my God.
You guys with me? Good, shut up. Okay. So if you jerk the cord, you get zero tension. You saw slack in the cord when I yanked on the rock. It continues going up with it's in free fall, going up for a split second. Little technical comment on force equations and vectors. If the mass of example 5 is accelerating down, we have two choices. We could always let down be negative. That gets confusing. You run into minuses. So what we're going to do is we're always going to take option B. We're going to let the direction of the winning or larger force always be positive. The physics is much more convenient. So, especially when we get to two-dimensional problems or many-body problems, we're going to let, hey, who's winning? That's positive. Losing is in the opposite direction, negative. Okay? Put your pencils down, look up. We're going to do a thought experiment. So you got about 15 minutes, questions to try, and I got some videos to show you as well, I think. Number 1, you can try. Number 1's a bit tricky. Number 1, you can try. Number 2 is good. 3 is algebraic, but we're physics 12. We can handle that now. Five is good. 7 is good. 9 is tricky, but good. Okay.